Welcome you all to the new session. Here we are going to see the next part of our finite state machines. Here in this session we are going to discuss about serial binary adder and as well as sequence generator. As a part of first topic, serial binary adder. Serial binary adder means we are going to add sequence of bits. For example, if I am having sequence of bits as 10 10 10 10 means for any as an example I am telling you as this as a sequence. Now this sequence has to get added up sequentially. Means 1 plus 0, that is 1, 1 plus 1, sum is 0, carry is 1, right? Next 0 plus 0 is 0, 0 plus 1, 1, 1 plus 0, 1. So these sequence need to get added up, and this carries also should be given as an addition for the next higher order bit additions. So we are going to see this kind of systematic approach, how we are going to perform under a particular sequence adding in this particular design. Now here you can see I am having two shift registers, first shift register and this is my second shift register. First shift register is having a value, that is this first bit I am considering to be A and next bit I am considering to be B here. So this is my B, second bit which occurs. So those two bits I am providing here directly. Through bits, through this thing, the values are moving as A and B values through a adding FSM, finite state machine, adder finite state machine. This adder is going to add these two bits, that is A plus B operation is performed under a adder. Now when A plus B operation is performed, a sum value is getting generated, that is S. That S value is stored in one of the shift register. Now shift register 1, shift register 2, the third shift register is getting stored the sum value here. Now here only sum value is not getting generated, there is a carry which is also getting generated, which need to be added to my next bit value. Why? Because this carry should get propagated for the next higher bit values also. That's the reason this particular value, this shift register, the value if you observe, the clock is given for adder as well as shift register. Now when clock is triggered at that particular point of time, this carry is also fed through our these channels, right? So all the three shift registers including my adder is working with a clock. That's the reason we call it as a synchronous serial binary adder or synchronous serial finite state machine we call it as. Now let us see how the process goes here. Now if you observe this one, this is S0 state and this is S1 state. Now S0 represents when carry in is 0, means carry value is 0. When carry is generated as 0, this I am going to represent as S0 state. So this is the state where carry value is 0. Now S1 is represents the carry is 1, means this S1 is a state where carry is equal to 1, right? So these are the two states which we have represented. Now see here, for example, I am taking my values as A, B, C and sum and carry. So carry 0 remains here for 0 0 0, that is 0 0 0 gives sum value 0, carry value 0, right? Next 0 1 1, 0 1 1 gives sum value as 0, carry value as sorry, this is 0 0 0 0 by 0, 0 0 1 by 1, this is 1 1 0 by 1. Now for the time sake I am removing this C value. So 0 0 gives sum 0, carry 0. For 0 1 sum gives 1 and carry as 0. For 1 0 sum value as 1, carry value as 0 here. So for all these three cases, for 0 0 0 1 1 0 case, my carry is remaining as 0 and my sum value is getting 0 1 1 for this particular case. So for carry 0 you got the answer why it is remaining in S0 state here. Now when it will travel to S1, whenever there is a carry C is equal to 1, it is getting generated. When it is going to generate for 1 1 combination, the sum value will be 0 and the carry will be 1, right? So you got carry as 1 here. So what happens is C0 to C1 it is going to travel with a sum value as 0. See, for 1 1 combination as input combination, you are getting output value as 0 here. That is 1 1 by 0 representation. So these kind of represent means input is 1 1, output is 0. So input by output is the representation that we are going to do for Mealy kind of machines. These kind of state machines we call it as Mealy kind of state machines. So input by output representation that we do on a transition. Now for Murray kind of machines, what we do when there is a transition between two states, 0 and 1. Now here 0 by 1 I am going to write, here 1 by 0 I am going to write. So input state by output value we are going to represent under Murray kind of machines. Murray type machines, what we are going to do, state by output value, state by output value. For 0 1 or 1 0 combination, this transition is occurring from 0 to 1, but what is the output value here? It is 0. Now from 1 to 0 when it is moving, whenever there is 1 1, so I am not going to I am just representing the input values on these transitions. We are not representing the output values as like this. So these are Mealy kind of machines. These are called as Murray type of machines. Under state itself, state by output, state by output. And on transitions we are going to just represent the input values. Whereas here on transitions we are going to represent input values by output value. And state contains only state values only, right? Now based upon this particular C is equal to 1, you can observe that it is going to remain in C is equal to 1 state for 0 1 combination, for 1 0 combination and for 1 1 combination, right? It is going to remain as the carry value is 1 here, it is going to keep its value constant over a period of time in S1 state. Now when it is going to back to S0 state, whenever 0 0 state occurs, what happens? The carry 1 state will move into carry 0 state here. So using this particular state diagram, we have drawn a state table also here. Now if you observe clearly, S0 for 0 0 it is remaining as S0, for 0 1 it is remaining in the S0 state, for 1 0 it remains in S0, for 1 1 it is in S1, for 0 0 again it is coming back to 0 value. Now these are your next state values, these are your present state, these are your output values. Now output value is sum. So sum for 0 0 is 0, 0 1 1, 1 0 1, 1 1 0 here, right? Now when for S1 what it is the value? S1 will S1 next state is S0. So that's the reason S0 it is writing here. And what is the for 0 0 it is coming to S0 input value, that's the reason it is written here. For 0 1 1 0, for 1 1, for all these three cases it is remaining in S1 only. So that's the reason it is mentioned as S1 S1 S1. Now here output of some value, that is for 0 0 it is 1 value, for 0 1 it is 0, for 1 0 it is 0, for 1 1 it is 1. So this is the representation of state table. State assignments, the same 0 0 conditions, what is the state assignment, state values? So 0 0 1 0. Why? Because the output values I am writing here. For S0 what is the value of output, for S1 what is the value of output, those values. Now for S1 the output value is 1 here, that's the reason I am writing 1 here. For remaining S0, for everything the output value got remain for one state, right? Now based upon this state diagram and state assignment table, we require this particular thing. Now if you observe clearly, we have a full adder with the two input bits A and B, and along with a flip-flop at the output side. What does a flip-flop do? Flip-flop is going to store the carry value, and P which is going to give as a sum value from the full adder. This carry value will be given as output. Again it goes back to full adder. Now for this full adder, what it does, it is going to add A value, B value and the C in value, right? So this is the logic diagram for our serial binary adder. Okay, let us see the next one, that is sequence generator. How the sequence is getting generated for our sequence to get produced. Let's see that one. This is a sequence generator. Now this sequence generator, see here, design a counter for the binary sequence generation of 0, 0, 1, 3, 4 and 5, 6. So those are the values. The number of flip-flops required here are, the maximum number given in the series is 6. So 6 can be represented using 1, 1, 0. Means I require 3 flip-flops. Because 3 bits can be stored under 3 flip-flops. Each flip-flop we can store only 1 bit of information. So that is the reason 6 is represented as 1, 1, 0, 1, 1, 0. So 3 bits are there. So we require 3 flip-flops here. So here we are going to construct this sequence generated using a JK flip-flop or D flip-flop, right? So I am considering the step 2. Step 1 we have seen number of flip-flops which are required for the sequence generation of 0, 1, 3, 5, 6. So that is the reason that maximum number is 6, so it is 6 is represented using 3 bit of information, so we require 3 flip-flops. What are the flip-flops we can use? JK or D flip-flop. So I am considering D flip-flop here. Step 2, excitation table for D flip-flop, that is outputs as input and input as output here. So 0 0 0 1 1 0 1 1. So you know the excitation table of D flip-flop, that is 0 1 0 1, right? Step 3 means how the sequence has to move. Now sequence has been given as 0 1 3 4 and 5, right? So 0, from 0 it is traveling to 1, 1 it is traveling to 3, 3 is traveling to 4, 4 is traveling to 6, again 6 it will come back to 0. Why? Because once it reaches the final state, it has to come back to its initial position to start the sequence again. So that is the reason from 6 it is going to 1. So this is the state diagram. We got the excitation table. In the next step we got the state diagram. Now let us write the excitation table based upon these particular two things now. That is, this is my present state, this is my next state. Now if present state is 0, if my present state is 0, the next state is 1. So 0 1. Now if present state is 1, next state is 3. So I am writing 3 here. So if present state is 3, next state is 4. So present state is 3, next state is 4. If present state is 4, next state is 6. So present state is 4, next state is 6. If present state is 6, next state is 0. So next state is 0. So this is the excitation table based upon my state diagram. Next, based upon this, we'll see the diagram, how we are constructing. Now see here, this is the Boolean expression. We are getting the Boolean expression here. Fourth step as a Boolean expression based upon the next state and previous state. That is QA, QB, QC. I have taken all the values and the don't care values also. Why don't care values? In the diagram you have seen clearly the present state, next state values. Now we have only these values. Apart from these values, there are some other values also there which are not represented. You have 0 1, you don't have 2, again 3 4 5 you don't have, 6 you don't have 7. So whatever the values which are not present here, I am considering them as a don't care condition. Now when don't care conditions are represented, see here, don't care I have taken for 1 0 1, that for is 5, 1 1 1, that is 7 as don't care. Next 0 1 0, that is 2 value as don't care. So whatever the values which are not there, I am representing them as don't care. So with the help of don't cares, I am rebuilding my expression for QA, that is QA exclusive with QB. Similarly QB complement, we got QB bar QC plus QA QB bar. Next for QC we got it as QA bar QB bar. So I got 3 Boolean expressions for my value. Those are represented as input values for DA, DB, DC. Right? Now these values I am going to consider as input values for my 3 flip-flops. We got 3 flip-flops, right? First flip-flop, second flip-flop, third flip-flop, 3 bit of information. Now DA value, you know, QA exclusive with QB. So I have taken QA exclusive with QB as input for first flip-flop. Next, for this one, I have drawn the logic circuit which is act as a input for the second flip-flop. This acts as the input for my third flip-flop. Now these 3 combinedly are given with common clock which is producing QC bar. Now this is a circuit which is going to generate the sequence of 0, 1, 3, 4 and 6. So this is what how we are going to represent the finite state machine representation, and we designed based upon our given requirement. Okay, thank you all.